In covalent bonding, atoms share electrons. So in this diagram on the right side of the screen, in the blue circles, I've got the nuclei, essentially, of each of the atoms in the bond. And you can see that in between the nuclei, it's shaded rather darkly. And that means that there is a rather dense negative charge distribution. There are lots of electrons that are held in between those two nuclei. And on the outside, the electron density is less dense than in between. Covalent, or molecular compounds, tend to be solids with low melting points, or liquids, or gases. What are some common gases? Oxygen, nitrogen, carbon dioxide. Those are all molecular compounds. They all contain nonmetallic elements. Covalent solids, anytime you hear the term covalent solid or molecular solid, the first thing that should pop into your head is butter. Molecular solid, butter. It has a low melting point and consists entirely of nonmetallic atoms. One shared pair of electrons, that is, two electrons, constitute a single covalent bond. So in this diagram, between the two nuclei, if there are two electrons that are being shared in here, that's a single covalent bond. If there are four electrons in between the nuclei, then that's a double covalent bond. And if there are three shared pairs, that is 6 electrons, then we say that these two atoms, the one on the left and the one on the right, are bonded by a triple covalent bond. The term bond polarity refers to the sharing of electrons between atoms. If the electrons are shared nearly equally, we call that a nonpolar covalent bond. If the electrons are not shared equally, in other words, if the electrons seem to spend more time around one atom than the other in a bond, then we call that a polar covalent bond. The electronegativity, which I'm going to abbreviate EN from now on, is the ability of an atom in a molecule to attract electrons to itself. You can think of electronegativity as kind of like a bowl of mashed potatoes going around the Thanksgiving dinner table. If the bowl of mashed potatoes spends roughly an equal time in front of each of the people at the table, that's kind of like a nonpolar covalent bond. On the other hand, if the bowl of mashed potatoes spends proportionately more time near your teenage son, who is a competitive swimmer, well, that's kind of like a polar covalent bond, in the sense that electrons spend more time around one atom than another in a polar covalent bond. A bonded atom with a large electronegativity has a great ability to attract electrons. With regard to the mashed potatoes, a teenage boy who is a competitive swimmer is kind of like an atom with a large electronegativity. A bonded atom with a small electronegativity does not attract electrons very well. The rest of us at the Thanksgiving dinner table don't attract the mashed potatoes particularly much. We can be considered kind of like atoms with low electronegativities. Of course, the electronegativity values have been tabulated. You should know that the maximum one is fluorine, and it has the value of 4.0. The minimum electronegativity is cesium, with a value of 0.7. Here are the electronegativities of the various elements, and if we look at the electronegativity difference between two elements, cesium and fluorine, cesium is right down here in the lower left, 0.7, fluorine up here in the upper right has an electronegativity of 4, so the difference is 3.3. Strontium, I'm circling right here, has an electronegativity of 1. Oxygen is 3.5, it's in the upper right, so that difference would be, of course, 2.5. Sodium is right here with an electronegativity of about 0.9. Chlorine has an electronegativity of 3, so its difference would be 2.1. Oxygen, we met already, an electronegativity of 3.5. Hydrogen, up here in the upper left, has an electronegativity of 2.1. So 3.5 minus 2.1 is 1.4. The difference between carbon and hydrogen in terms of electronegativity, carbon is 2.5, hydrogen is 2.1. So that's a difference of 0.4. In a hydrogen-hydrogen bond, of course, the difference between the electronegativities of the two atoms would be 2.1 minus 2.1, which is obviously 0. So, for any two atoms on the periodic table, we can calculate their electronegativity difference. And that electronegativity difference between bonded atoms approximates the type of bond between them. If the electronegativity difference is less than 0.5, we consider that a nonpolar covalent bond. If it's between 0.5 and 2, we consider that a polar covalent bond, and if it's greater than 2, we tend to consider that an ionic bond. The difference in electronegativities is a continuum, and we have drawn lines as to where we're going to call a nonpolar covalent or a polar covalent or an ionic bond. As the difference in electronegativity increases, the bond polarity increases. CH bonds have an electronegativity difference of 0.4. So if you look at our first statement right up here at the top of the screen, if the electronegativity difference is less than 0.5, that's considered a nonpolar covalent bond. As you can see on the right side of the screen, I think it would be a good idea for you to memorize that carbon-hydrogen bonds are nonpolar, and of course, any bond between identical types of atoms would be nonpolar because the electronegativity difference would be 0 for those. Final thoughts on covalent bonding. Covalent bonding occurs when atoms share valence electrons. If 2 or 4 or 6 electrons are shared between atoms, a single, double, or triple covalent bond exists. 2. If the electrons are shared roughly equally, then a nonpolar covalent bond exists. Such bonds exist between identical atoms and between carbon and hydrogen atoms. 3. If the electrons are shared unequally, then a polar covalent bond exists. And 4. The difference in electronegativity between atoms can reveal the type of bond. So as you can see at the bottom of the screen, if the electronegativity difference is less than 0.5, that's a nonpolar covalent bond. If it's between 0.5 and 2, that's a polar covalent bond. And if it's greater than 2, that's an ionic bond.